Welcome to the deep dive. Today we're looking at a pretty cool piece of engineering, the DVIGear DVI-7317.
Right. It's a 4K HDMI fiber optic extender.
Exactly. And our mission, really, is to unpack a very specific problem it solves. How on earth do you get a flawless 4K video signal over like a mile of distance?
And this is the key, using just one single strand of fiber, not two, just one.
So let's lay out the basics. It supports HDMI 1.4, resolutions up to 4K.
3840 by 2160, and there's an important detail there. You can get that at 30 frames per second with perfect 4.4.4 color.
So uncompressed color information.
Exactly. Or you can push it to 60 frames a second, but you have to drop the color data a bit to 4.2.0.
Either way, you're still looking at a huge data rate.
Yeah.
The spec says 10.3 gigabits per second.
That's the aggregate rate, yeah, flying from the transmitter to the receiver.
Okay, so let's get right into the engineering puzzle. If you have 10.3 gigs flying one way from A to B, how does B talk back to A? You'd think you'd need a second cable for that.
You would, and that's where the magic is. The solution is something called wavelength division multiplexing.
WDM.
WDM, yeah. Look, the easiest way to think about it is like a two-lane highway where both lanes are. Well, they're physically in the same space.
How does that work?
It uses two totally different colors of light, two different wavelengths on that one single fiber, specifically 1310 nanometers and 1550 nanometers.
So the main video signal is zipping along on one color,
Uh-huh.
and the return communication is on the other color at the exact same time in the same cable.
And they don't interfere with each other at all. It's brilliant.
So what's actually coming back on that return path? It can't be much.
No, it's a much slower 250 megabits per second. But that's more than enough for what it needs to do. It's handling things like EDID.
The extended display identification data. So the monitor telling the source what it's capable of.
Yes. And critically, it handles HDCP pass-through.
And just to clarify for everyone, HDCP is high bandwidth digital content protection. It's that constant digital handshake you need to play a Blu-ray or stream Netflix.
Without it, the screen just stays black.
Exactly.
And you know, speaking of HDCP, this brings us to the really staggering part of the specs, the distances this thing can achieve.
It's a massive trade-off, isn't it? There's a huge penalty for turning that encryption on.
It's enormous. If you need HDCP, say you're in a commercial movie theater, your max distance is capped.
At what?
About 1,000 feet, or 300 meters. And it doesn't matter what kind of fiber you use. It's a hard limit.
Okay. But what if you don't need HDCP? Like in a, I don't know, a secure government facility or something.
That's when the numbers just get wild. With single-mode fiber, you can push that 4K signal over 1.2 miles.
1.2 miles. That's almost 2 kilometers.
It is. I mean, to put that in perspective, that's like 20 football fields laid end to end.
That's just incredible. And the practical benefit there isn't just about the distance, is it? It's about using fiber in the first place.
Right. Fiber is completely immune to environmental signal noise,
RFI and EMI.
radio frequency, and electromagnetic interference. So if you're running this cable next to heavy power lines or sensitive medical equipment, the signal is perfectly clean. It's a huge advantage.
So to sum it up, we have an incredibly elegant solution here. WDM lets you push high-speed 4K over huge distances on one fiber, and it's super efficient too, only uses about 1.7 watts.
It's a very neat package. But it leaves us with a really fascinating question to think about.
The HDCP problem.
The HDCP problem. So here's something for you to mull over. The hardware is physically capable of sending a signal over a mile, flawlessly.
Okay.
But when you enable a standard software feature, that HDCP encryption, you lose over 80% of that distance. Why?
So it's not the fiber, it's not the laser, it's the encryption itself.
It suggests the continuous, time-sensitive process of encrypting and decrypting the signal introduces just enough timing jitter or maybe error correction overhead that the optical link can't handle it over that full distance. That massive difference just from flipping a software switch shows you exactly where the real engineering limits